Hi, I'm Mike Ryan. Today we're going to talk about the geology of turquoise. Now, let me start off with the disclaimer that I'm not a geologist. I'm certainly not an expert at geology. The extent of my knowledge probably goes to Geology 101 course that I took my freshman year in college. But I did get an A in it, so maybe that'll be good enough for this video to talk a little bit about geology of turquoise. But there are a lot of you out there who know much more, and I would certainly defer to your knowledge. Geology is a science that deals with the Earth's physical structure and its substance, the history of it, and the processes that acted upon it, all the separation of the continents and the movements of the plains and all of this that takes place over unimaginable time periods. Gemology, on the other hand, is the science of studying, cutting, valuing, and identifying different gemstones. Now, anytime you get into science, you can very quickly walk off the edge there and get into some real deep technical issues. And I think that's really true about turquoise. It's not really studied that much. I mean, comparing to petroleum geology, because there's a lot of money in oil, not so much in turquoise. So you don't see these big studies funded by big corporations and about turquoise. But we'll go through it a little bit and see if we can keep the science to a lay person's level and really keep it as simple as possible, but just enough so we're really capturing some accurate information. The first thing to know is turquoise is a secondary mineral. It is formed from the breakdown of other minerals in its host rock. And it's not present in the original copper porphyry. So it wasn't there, something happened, and then it's there. Now, porphyry is a big word that means a hard, igneous rock containing crystals, usually of feldspar, in a fine-grained, typically reddish ground mass. And we find a lot of turquoise where we find copper, and it's that in that copper porphyry where the copper ore is extracted. Turquoise forms when groundwater from rain or snowmelt percolates down through the Earth's surface, and it comes through the copper porphyry, and the dissolved oxygen in the water oxidizes the copper sulfides into copper sulfates, soluble sulfates. And this acidic copper-laden solution, there's the recipe for turquoise, if you will, then has to find a place where it can sit for a long period of time and kind of cook and form into turquoise. And it does that in between the veins between different rock formations or in clay pockets, because in the rocks there it's protected from more acidic rain coming in and destroying the solution before the turquoise forms, or the clay pockets will also protect it. So that's why we have vein turquoise and then we have nugget turquoise. The nuggets form in the clay pockets, and that's why we'll often hear the term a pocket mine. So it takes a long time for this recipe, this solution to form into turquoise. And it does it at relatively low temperatures. Low for geology terms, meaning 300 to 400 degrees. We get into the actual nomenclature, the formula of the turquoise, and we're going to see here that there's a family, a turquoise family, and they're all within the hydrated aluminum copper phosphate group. And these are turquoise, faustite, and chalcosiderite. And we see here the chemical formula for these. Has the aluminum, has the phosphorus. There is a phosphate, and there's a hydroxide. I believe that's the OH. The difference being there's the copper with the turquoise. There's the copper, but you have the addition of zinc with faustite, and then either copper or the iron ion with chalcosiderite. These additional elements, the zinc and the ferrous, will affect the color, with the zinc giving more of this lime green color we associate with faustite, and the ferrous generally being associated more with the green colors in turquoise. Turquoise runs in hardness between a 5 and a 6 on the Mohs scale. I think some people would say maybe it gets as high as 6.5. I think anybody who says 7 is really pushing it. And that hardness would come from the silica that is in the host rock that makes that hardness, and also the ability to take a fine polish. It is a cryptocrystalline mineral, which just means it's a rock. So the way the formation, it binds together, it doesn't form crystals where you have specific angles of formation, except in one area that we know of, which is in Virginia at the Bishop's Mine. And we see here a beautiful example of turquoise crystals. I mentioned that the turquoise needs to have a place to rest while it becomes turquoise. And that's usually either in the fissures, it forms veins, or in the clay pockets where it forms nuggets. Occasionally, it will form within a fossilized organic organism. And so the most common ones being bipods, clams, if you will, and eggs. And because it's formed so long ago, we think most of these eggs were probably dinosaur eggs. It also forms within the fossilized marine organisms. Now, the most famous one, turquoise that we call fossil turquoise, formed within these marine organisms, these tubular marine organisms, is the fossil turquoise from Lone Mountain that we see here in this beautiful necklace by Charles Lolema. It's very rare. As far as the clams, Caracal Lake is the most well-known that I know of for finding these fossilized clams. And we also see one example of a turquoise forming within the recess of a fossilized egg. Is it dinosaur? Is it some other? I don't know. I was told it was dinosaur. Maybe it is. I don't know. All of these are known as pseudomorphs. Now, there's the question of supergene, which is top down, and hypogene, which is bottom up. And this just means where the water solution comes from. Does it percolate down from gravity, from the surface, or does it come up from below through groundwater from below and come up? If it's from the top, as we might imagine, it only goes down maybe 60 feet or so. So most of the turquoise that we find at the shallower depths, we generally consider to be supergene formation. But we know turquoise has been found at hundreds of feet. So it goes to reason that this may be coming from hypogene formation. Although it does get a bit confusing because, you know, the rocks all move around. So who knows? Maybe it formed as supergene and moved down, or hypogene moved up. These are beyond my pay grade when it comes to geology. The age of turquoise. In Turquoise in America Part 2 in the appendix, we were really fortunate to get a description of turquoise at Bisbee from Richard Graham, who's the former chief geologist of Phelps Dodge. He was in charge of the pit during the time period when turquoise was discovered at the Lavender Pit. And this was between 1950 and 1975, although most of the turquoise was all mined within the early period between 50 and 53, because they very quickly got down below the turquoise zone, which is in the glance conglomerate. Glance conglomerate, as the name implies, are just little pebbles that are just kind of stuck together, kind of cemented together. Very crumbly, unstable sort of formation. And that was formed 145 million years ago, although Dr. Graham says that the turquoise formed only 17 million years ago or less. So we can use as a rule of thumb that turquoise generally is going to be formed wherever it's deposited between 1 million and perhaps 30 million years old. So I hope this brief overview of the geology of turquoise has been of some interest to you.